So for these kinds of calculations, what we can see is that we either have masses of substances, which we need to convert to moles, which is our version of a particle count, or we've been given the number of moles and are being asked to calculate the mass of the substance. So in the first one here, we have 34 grams of magnesium was weighed on a balance. How many moles of the substance has been measured out? So here we need to be using the equation where we were relating number of moles to mass. And here I have N equals M over MM, where N is our number of moles, M is our mass, and MM is the molar mass, which comes from the periodic table. Give me a second. So I have the periodic table on my computer screen in front of me. You should have your table out in front of you on paper as well. What I can see is that for magnesium, which is number 12 on the table, I can see that its molar mass is 24.305, and that's measured in grams per mole, meaning that if I had a mole of magnesium, it would weigh 24.305 grams. Now, we should be able to notice that we have more than 1 mole of magnesium. The mass that we've measured out here is significantly larger. It's 10 grams more, which means when we do a calculation at the end, the number of moles should be exceeding 1. It shouldn't be. It should be smaller than 2, but larger than 1. But we'll actually have to undergo the calculation to get the exact value. So what we know so far is the mass of the substance, and that's 34 grams. We also know the molar mass from our periodic table, and that is 24.305 grams. What we don't know is the number of moles, N. So all we're going to have to do is do a straight substitution. The number of moles will be equal to 34. Excuse me, I've written that the correct way. My bad. It's a bit early in the morning for me. Divided by our molar mass, which is 24.305. Now, if I put that into my calculator, I'm going to put up a fraction. So that is 34 over 24.305. And that is equal to 1.4 moles. Now, I've done this to two significant figures, not something that I'm covering in any great detail in this video, but certainly something that we can talk about when we're doing calculations in class time. But I have matched the number of significant figures here to the lowest measurement that we used in our calculation. Now, that calculation was fairly simple. This one introduces a couple more steps. What I have here is that we have 2.5 moles of ethanol, and I've given the formula here as well. This isn't something that you would have to know off by heart at the moment, probably something that you would need to know by, say, HSC time, but for now, I'll give you the formula, and that should be fine. Was collected in some sort of reaction or experiment, and the question is, what is the mass of the ethanol? So what we need to be doing is using N equals M over MM. Now, we know the number of moles, that's N, and it's 2.5. Now, molar mass can always be calculated, and I'll show you how to do that in a moment. It's not something that's particularly unknown, but what we're trying to find is the mass of the substance. Now, at the moment, M is not the subject, so similar to the other equation that we were using before with number of particles, we need to rearrange so that M is our subject, the mass of the substance. So I'm going to multiply by molar mass on both sides. And to rearrange the equation, it should look something like this. That the number of moles is equal, the mass of the substance is equal to the number of moles present times the molar mass. Now, to calculate molar mass, I'm going to be doing that over here. For ethanol, we have 3 different substances. We have carbon, which has a molar mass of 12.01. So I'm going to write that like that. The molar mass of carbon is 12.01. We also have hydrogen, and its molar mass is equal to 1.008 grams. And the molar mass of oxygen is exactly equal to 16, I believe, or 15.99, depending on what periodic table you're looking at. I'm just going to run with 16.00. For the time being. So we have all these molar masses, but what we should notice is that in this in this particle, all of those all of those atoms exist in different ratios. There's 2 carbons for every hydrogen for every oxygen, which means if I have a mole of this substance, I would need to multiply up the masses of all of these substances here. So for example, I would have double the mass of carbon because I have 2 carbon particles in a molecule. I would have to multiply my molar mass of hydrogen by 6 because I have 6 particles in every molecule, and I would have to just add 1 single mass of oxygen here. So the molar mass of C2H6O, or ethanol, is equal to, and I'm going to put all of this in brackets, 2 times 12.01 plus 6 times 1.008, which is the molar mass of hydrogen. And for the oxygen, I would just have to write 1 times 16. Now, putting all of that in my calculator, in brackets, where are my brackets? They're here. 2 times 12.01. Oh, hit some buttons on the way. Give me a sec. Get rid of them. 2 times 12.01, close bracket, plus 6 times 1.08, plus 16. I'm not going to worry about the brackets because it's just going to come out as 16. And that gives us 46.068. I can now include this on my little data column that I put over here, 46.068, and I can include that in my calculation when I substitute in. So I have 2.5 moles of substance, and I'm going to multiply by 46.068. Again, I'm going to calculate that. So my original answer times 2.5, and that's equal to 115.17, and that's the number of grams that I have of ethanol if I've collected 2.5 moles of the substance. Now, my final question here is, what is the mass of 3.47 times 10 to the 20 copper atoms? So at the moment, I've been given the number of atoms here, n. N is equal to 3.47 times 10 to the 20. Just seeing the number of particles, what we should assume is that we're going to need the Avogadro constant as well. But what we don't know is the number of moles. And from there, if we knew the number of moles, we'd be able to calculate the mass of the substance using our mass and molar mass equation. So mass is also unknown, but our molar mass is just for plain copper atoms. And if I look at my periodic table, I can see that the molar mass of copper is 63.546. So I'm going to put that in immediately. This doesn't have any special formula. It's just single copper atoms with a molar mass of 63.546. So for this question, we're going to have to do 2 calculations in short succession. We're going to need our N over Na calculation and our M over Mm calculation as well. So the one that we're going to be doing first is that the number of moles is equal to N over Na, and we're going to calculate for moles to begin with. Now to do that, what we'd have to do is just substitute in quite simply. So 3.47 times 10 to the 20, all divided by 6.022 times 10 to the 23. I'm going to put that in my calculator. Bring that down. Clear that. Fraction first. 3.47 times 10 to the 20 divided by 6.022 times 10 to the 23. So I have, and this would be 5.76 times 10 to the negative 1, 2, 3, 4 moles. So 5.76 times 10 to the negative 4 moles. And then what we need to do is calculate for the mass. And we already did this in the other calculation. Get this out of the way. It's making everything a little bit bright. So in the other calculation, what we saw was that if we were trying to find M, we would have to rearrange our equation and write N times MM. So if I substitute in, that's 5.6 times 10 to the negative 4 multiplied by my molar mass, which is 63.546. So again, I'm going to put that into my calculator. So 5.6, and it was 76, excuse me. 5.76 times 10 to the negative 4 multiplied by 63.546. And what you'll notice at the end is when I write this answer, so it's going to be 3.66, and that is going to be times 10 to the negative 2 in grams. Notice that I have reported this to 3 significant figures, and that matches the piece of data here that's to 3 significant figures as well, with the lowest number of significant figures. So that concludes today's lesson with those calculations. That should hopefully give you a little bit of an idea of how we can use the mole concept to calculate both number of particles and masses of substance, or vice versa. And that even though there isn't a formula that we use that directly relates the mass of a substance to the number of particles, we are able to use the two formulas that we have used today to convert between the two. Now, in the next lesson, what we're going to be looking at is the percentage composition of elements in compounds. Now, we've done percentage composition calculations before for parts of a mixture, but this will be if I have a compound, what percentage of mass is contributed by each of the elements. But until then, have a good one.